Hi guys, this is Mr. Adams from Middle High School, and before we jump into electrolytic cells, I just want to tell everyone to please be safe and follow the guidelines, okay? Alrighty, now we did the voltaic cell recently, right? And now we're looking at electrolytic cells. Now electrolytic cells come in two flavors. They can do something called electrolysis and something that could be called electroplating. Electrolysis, lysis, the word is a Greek word, to lyse means to break apart, right? So you can break apart a compound into its elemental form, and is used very widely in industry. And electroplating, right, is used to plate objects, either to protect them or to make them look more valuable. For example, you've heard of like gold-plated jewelry or silver-plated jewelry and so on, right? Okay, now in the electrolytic cells, guys, okay, they're slightly different, well, a lot different from the voltaic cells. For example, in an electrolytic cell, it's a non-spontaneous reaction, right? Which is being, okay, driven, okay, or pushed by an outside power source. And normally the outside power source is a battery, okay? Alrighty. Electrolytic cells have only one chamber, and they do not have a salt bridge, okay? So for example, over here, right, it's my fancy setup. There's only one container, one beaker, one chamber, right? And there's no salt bridge, okay? All right. Now, in electrolytic cells, there is an anode and there is a cathode. But make a note, guys, okay? The anode in the electrolytic cell is positive and the cathode is negative. Remember, in the voltaic cell, right, the opposite was true, okay? All right, we'll look at that in a second. Now, the nice thing is N-ox, red cat still apply. So oxidation takes place at the anode and reduction takes place at the cathode. Okay, and also in electrolytic cells, sometimes, right, they use inert electrodes. Now, what does that mean? What does inert gas mean? Okay, from Chem 1. Now, simply what they're saying, right, in terms of inert, they mean that the electrodes themselves, right, are not involved in the reaction. So these two funny pencils I used there, no, the pencils inside of them are graphite, right, which is basically carbon. Okay, so I'm going to use those on my inert electrodes. They won't be caught up in the reaction. Remember, in the voltaic cell, the anode got broken down, right, and the cathode got built up, got more mass. But in this particular cell right here, this cell I'm going to set up today, the carbons will not be in your half reactions. Okay, so before I move on and set this up, let's review really quickly the voltaic cell. The voltaic cells are what? They are spontaneous. Okay, you put it together and it moves forward the direction naturally, okay? And it produces electricity, right? And we agreed that's the principle behind a battery. Okay, voltaic cells have two chambers, all right? And they have a salt bridge, okay? Remember, the ions flow through the salt bridge, and the chambers have solutions of ions in them. The anode is negative in the voltaic cell, and the cathode is positive, right? Okay, and ox, red cat, applies also for the voltaic cell. All right, guys, so here's what's going to happen. I have this guy right here. Okay, it's my potassium iodide, Ki, all right? I'm going to make it into an aqueous solution, okay? Now I'm going to put it inside this chamber right here, and I'm going to hook these wires up, okay? I got two wires right here. Remember, electrons flow through wires, yes? Okay. Now, my battery, folks, I don't know if you can see it or not. See that positive right there? Terminal right there? So that determines the anode from the cathode for me. Now, remember, in the electrolytic cell, right, the anode is positive. So this terminal right here, this positive terminal, tells me that's the anode in the electrolytic cell. This guy, this negative terminal right here, tells me that's going to be the cathode. So I know automatically where oxidation and reduction takes place based on the charges on the terminals of the battery in the electrolytic cell. Now, ideally, folks, I would have wanted this guy right here, or the salt I'm trying to do with the electrolytic cell, to be in a molten state, right? Melted state. But the funny thing about ionic compounds, right? They have a really high melting points. So it's very, very hard to, for me on a normal level to do that, right? Industry, they can do it, no problem. But I don't have the energy in terms of the power source to melt this potassium iodide or sodium chloride or whatever, right? So I'm going to make it aqueous, right? Okay, and we'll go from there and see what happens. So I'll be back in a second. All right, guys, I'm back, okay? And my setup seems to be working. We have success. Okay, so let's recap. We have one chamber, right? Okay, and in this one chamber right here, we have our aqueous potassium iodide solution, okay? Now, these two funny pencils, those are my electrodes. Now, how do you know the anode from the cathode? We simply look at the terminals of the battery. Remember, we said the anode, right, is going to be positive, okay? And this terminal right here, okay, over here, okay, the negative terminal, that's our cathode. And remember, guys, anox, red cat still applies. Now, I want you guys to look at this carefully. I know it's kind of hard to see. Do you see over here, this guy right here at this anode? You see that funny brownish color being formed right there? That right there, folks, is iodine being formed from the potassium iodide in solution. That's iodine being formed. Okay, so an oxidation reaction is taking place where you have the iodine, which was negative, right, in the Ki, and is forming I2 0. Okay, so even if you go from negative to 0, your oxidation number is increasing. Okay, therefore that's oxidation. So iodine is being oxidized in this case right here. Now the funny things, folks, because we have it in water, right? We have water in the solution competing with the potassium. So the funny thing is the potassium didn't get reduced, right? The elements in the water got reduced. Let me show you something real quick. Let me try something here. I have some, what's this, pH hydron paper, right here. Can you see this? Okay, pH hydron paper with these different pH values on it. So let me put it right here. Now what I'm going to do, I'm going to take a piece, right? I'm going to poke it inside the water, the solution. Okay, so let me see. All right, put it to that electrode right there, dip it in. Okay, all right, see that? Bam. All right, so let me see what pH is that. See that right there? That says pH 10. Now what ion, folks, what ion would give you a pH of around 10? Do you remember from acids and bases? Yes, the answer is hydroxide, OH minus, right? So the reaction that's taking place here at the cathode, right? Something's being reduced in the water to give you hydroxide. No, I don't want to get too much into that. We can talk about that later on, right? But we have success. We've produced iodine, okay, I2 on the cathodes, on the anode side. Anode side, we've produced I2, iodine, and also on our cathode side, we've produced a hydroxide ion. So let's try this again. Let's take this, another one of these bits of paper, and let's stick it on this side, okay. Alrighty, so you see, okay, it's a bit contaminated, but see, there's a different value there. All right, folks, as always, hard work plus sacrifice equals success, okay? We got our iodine, our brownish guy right there, so they're mixing together now. And on this side, guys, we produce hydroxide. So hydroxide this side and iodine this side. Be safe, guys. Take care. And as always, guys, we're going to get through this, okay? Alrighty.